Welcome to the course on design of power electronic converters. Today we will begin with the next module, and that module is of gate drivers. So, the first lecture I'll be just introducing gate drivers. Any power semiconductor device, basically your MOSFETs and IGBTs that which we use very frequently, they are connected with the driver, and then that driver gets the signals from your controller. So, the controller may be an analog controller or a digital controller, and in terms of digital controller it may be microcontroller, DSP or FPGAs. So, then what happens is that you have these kind of PWM gate pulses which are given by these controllers, and these are usually of lesser voltages, let us say of 0 to 3.3 volt or 5 volt, like that. And then so these cannot drive these MOSFETs and IGBTs because their voltage levels are usually low, and also these controllers they do not have the ability, the current they cannot sink that much current or supply that much current which is sufficient enough to drive these MOSFETs or IGBTs. So, in between we require another circuitry which is called as the gate drive circuit, and this kind of acts as an interface between this controller and the power semiconductor device. And usually you will be having a gate resistor in between. So, this is like this kind of a gate resistor which is there, it is usually denoted by RG, and that gets your voltages or signals from this gate driver, and there are different types of drivers which are used. So, now let us understand it in little bit more detail. So, here I have taken example of one leg of an edge bridge. So, this is the DC supply which is connected to this one leg, and then we have these two IGBTs with anti-parallel diodes, and then there are two gate resistors RG1 and RG2, and we have two gate drive circuits. This is your driver 1 and then this is your second driver 2, and these drivers they are receiving gate pulses from this controller, and let us say those are named as VPWM1 and VPWM2. And then here there is a common ground because this controller will have its own reference with respect to which it will be giving these pulses, PWM gate pulses. So, this is the common ground which is denoted in this green color, and that ground is also connected to these drivers input side, both the input side of driver 1 and driver 2. So, let us see what is the picture over here in terms of the reference that we are using. Now, we have studied this while discussing your semiconductor devices, that the voltage that we have to provide is with respect to the emitter on the gate, and then we can drive the IGBT or the MOSFET. So, here then this has to be the reference, the emitter has to be the reference with respect to which the voltage has to be applied on the gate terminal. Now, so we have to understand how this voltage of this emitter point E1 and this emitter point E2 that changes or it does not change. We have to understand that. So, for that let us say, let us give some name to these transistor. Let us call this transistor as T plus and this transistor as T minus. So, when your T plus is on, T plus is on means your this upper switch is on. So, then what will happen is that let us assume it to be ideal. So, at that time this we can consider it to be a short, and so when it is a short, so what will happen is that this voltage over here at this point, this emitter point's E1's potential with respect to this bus will become equal to VDC. So, let us call this terminal as N and this bus as P. So, we will be having your voltages V C C2N, if we write it, that will be equal to VDC. This is VC2, the potential over here with respect to this, that is equal to VDC, and your VE2N, that is equal to 0, because this is always connected to this N point, alright. Now, what is the potential of VG2N? So, VG2N will be equal to whatever is the voltage that is required to turn this IGBT off, because when T plus is on, your T minus is off. Now, let us say that a typical voltage of plus 15 and minus 7 is what is applied to turn on and turn off the IGBTs. So, that means this is plus 15 volt that is given to turn on the IGBT and minus 7 volt that is given to turn off the IGBT. So, in that case, your gate voltage over here will be minus 7 volt. This point's potential will be minus 7 volt with respect to E2 or with respect to N. So, what we will be having is this voltage will be equal to minus 7 volt. Now, let us see the status for the other upper IGBT. So, VC1N will be equal to VDC, okay, and this point's potential will always be equal to VDC because this is always connected to this bus P. Then next is your VE1N. This emitter's potential with respect to this bus N, that is your VE1N. So, that is equal to VDC because we assume this is on and so this is shorted. After that, you have your VG1 E1 that we should find out what it should be. Now, with respect to this emitter, to turn it on, G1 has to be 15 volt, that's what we have taken here to turn it on, okay. So, then this will be equal to plus 15 volt. And if we see VG1 with respect to N, so that will be equal to plus 15 volt plus VDC, because over here this E1 itself is at the potential of VDC. So, with respect to N, E1 is at VDC, and with respect to E1, G1 is at plus 15 volt. Now, let us see the potentials when T minus is on, that means your lower switch is on. So, when T minus is on, your VC2N, this becomes equal to 0. This is because if T minus is on, this is shorted. So, C2 also gets connected to N point, and your VE2N, that will be equal to also 0, and this will be always equal to 0 because this is always connected to N. Then we have this VG2N, that will be equal to plus 15 volt, because here we would we are turning it on. So, this has to be plus 15 with respect to E2. Then we have VC1N, now this will be always equal to VDC. Then VE1N, now this is going to be equal to 0. Now, this is why this is 0, because this is shorted. So, this point's potential, E1's potential is now connected to here, which is N. Further, your VG1 E1 now will be equal to minus 7 volt, because this is off. So, G1 has to be minus 7 with respect to E1, and your VG1N, this will be equal to also minus 7 volt, because you can see that E1 itself is at 0 potential. So, therefore, G1 is also at minus 7 volt. All right. So, if we plot it, this is how your plot will look like. So, VPWM1, these are with respect to your ground. So, that means with respect to this ground, VPWM1 and VPWM2. So, that is, let us say, equal to your 3.3 volt or 5 volt, whatever small it is giving, this is 0. And similarly, VPWM2 will also be like that with respect to the same reference, which we have denoted as ground. Further, your G1 E1 with respect to E1, that means your this point G1 E1 with respect to E1, that is going to be equal to here what we have taken as typical voltage of plus 15 volt and minus 7 volt is what is going to come. And similarly, here for V G2 E2 as well, what we observe is that this G2 E2, this will be also plus 15 and minus 7 with respect to E2. So, this is going to be your plus 15 volt and this is going to be your minus 7 volt. But if we would have plotted this as your VG1N capital N and here VG2 capital N, means your with respect to the reference bus N, the common reference bus, negative bus N. So, there this would have gone from plus 15 volt plus VDC, and this would have remained at minus 7 volt, whereas for VG2N it remains the same. Okay, so this would have what it would have become your VG1NS, right. Now, so if your VDC was, let us say, 500 volt, so this would have become 515 volt and minus 7 volt. So, what we observe is that your since your emitter's potential is floating for your E1, the upper IGBT, so your gate driver's potential that changes by huge amount as you turn it on and turn it off. So, this kind of a voltage with respect to your reference bus N, it will be very difficult to generate for the upper IGBT. Whereas for the lower IGBT, it should not be that difficult because the emitter is not floating for the lower IGBT. So, what we observe from here is that it depends on the position of the transistor in the circuit and what kind of circuit you may be having, different type of topologies are there, and depending on that your IGBT or your MOSFET, whatever transistor you are using, its location in the circuit and how it is turning on and turning off, and how the potential of the emitter or the source are changing, whether it is floating or non-floating. Depending on that, your gate driver's voltages also has to be changed. Okay. So, then this is a problem. So, that means we have to have an interface circuit in between which can do the isolation and which can give voltages with respect to a floating reference. So, that is what your one of the jobs of the driver, because of which we use it. Then one more thing that is that you should note down is that this gate emitter region has its own requirement. Now, here I have taken plus 15 minus 7 volt. Now, always it may not be plus 15 minus 7 volt, different voltages may be required to push it into the ohmic region or the saturation region. So, so the driver should be capable enough to be able to give that much voltage, and also there may be a driving current requirement, whatever is this gate requirement Ig over here, which should be sufficient enough to drive this gate emitter region. It should be able to provide the charge Qg that is required to turn on the gate emitter region, and also it should be able to sink that much of current when we are turning it off. So, that is also something what the driver does and is what why we need it. So, now let us look into some of the requirements of the driver which the driver has to satisfy. So, this is the driver, which is represented by a box here. So, this is your driver. So, what we understood from the edge bridge, one leg of the edge bridge example, that it should be able to provide the isolation. The driver should be able to provide isolation. Why? Because here this reference, which is your ground, this may be connected to the controller, and it's a fixed potential, whereas here what we will be having is that this reference is with respect to this emitter, and this may be floating. Okay. So, it should be able to provide the isolation, and next is that it should be able to meet whatever the voltage requirements that may be between the gate and emitter, and also provide the current requirements of the gate emitter or the gate source region. So, first requirement is that it should meet the voltage and current requirements of the gate emitter or source region. Second, it should also be able to provide isolation. Now, this isolation may be a magnetic isolation or it may be an optical isolation. Sometimes isolations are not given also, but usually we will take it that some kind of isolation, it's good to have that. Then next is that it should be able to work with floating supply. Now, why we are talking about floating supply over here? Because here this point, emitter point, this is floating, this may be floating. As we saw in the edge bridge example, one leg example, the lower IGBT's emitter is not floating, but the upper IGBT's emitter is potential is floating. Okay. So, the driver should be capable of working with floating supply. That means whatever is giving supply to this driver on this output side, So, let us say that is Vg, that is going to give its voltage with respect to this reference, which is your emitter or source, which may be floating. So, it should be capable of working with floating voltages and floating supplies. Next, it should be able to do the level shifting. Now, what do we mean by level shifting? It is just very simple, that it should be able to shift the voltage level. So, if let us say this is for your 3.3 volt, which is your VPWM, which is applied over here, VPWM. This is what comes to the input side of the driver, and the output side of the driver, it may be a different voltage that may be given. Okay, and that may be your plus Vg plus 15 volt, 12 volt, 12 volt, 18, whatever is the requirement of that particular IGBT or MOSFET, and you may give some small negative voltage also, depending whether it is a MOSFET or an IGBT. So, it should be able to do the shifting in the level. So, that is your level shifting. And next, it should give a high impedance input. Now, why we are telling that it should have a high impedance input? Now, note that this side of the driver is connected to the controller, and this usually does not have very high current sinking or supply ability. So, then what will happen is that this is connected to this over here, and if it is going to draw a lot of current or sink a lot of current, so then that will load the controller, which is not desirable. So, over here whatever is the resistance that we see, this should be high enough. Okay. So, high impedance input it should provide. Alright, and of course, at the same time output side it should be able to provide whatever is the gate current requirement or whatever is the gate to emitter voltage requirement, that also it should be able to provide. So, low impedance output and high impedance input, that is what the driver should be able to should provide. So, the key points of this lecture is that we require a gate driver circuit in between the controller and the power electronic device. And what are its main job? It should do level shifting, it mostly provides isolation, and it should be able to work with floating supplies, and then it should the most important is that it should be able to supply the current requirement and the voltage requirements of the IGBT or the MOSFET, and it should also provide a high input impedance. Thank you.